Okay, so here's what we were talking about last time. We were doing Green's theorem, and this is a picture that gets at one of the fundamental reasons why Green's theorem works, and that is that this idea. We're looking at. If I can get my thing to work here, there we go. We're looking at boundary line integral. This is the object of interest that I claim is an accumulating quantity, is the vector line integral of some given vector field around the boundary of some region, right? And this boundary line integral, we argued last time, is an accumulating quantity, and it's an accumulating quantity because of the fact that the boundaries themselves are accumulating. So specifically, this boundary plus this boundary, when you add them, notice that this shared edge here, that shared edge appears twice with opposite orientations. Now let's say that in terms of the line integral. The line integral as part of the boundary of the left piece and the line integral as part of the right piece are line integrals on the same curve in opposite directions. Right? And so the sum of that green piece of line integral plus that blue piece of line integral is 0. Right? When you add up that line integral, around these boundary curves, the terms associated to this piece right here just cancel each other. Right? So altogether then, this boundary plus that boundary plus that boundary, when you add up all these boundaries, which you can think of as adding up line integrals around those boundaries, all of these interior pieces disappear. This edge, gone. This edge, gone. Appears twice. Opposite orientations, right? So this edge, gone. All of these edges that are slices that you made when you sliced up the region. The act of slicing means that there was region on both sides, and again, opposite orientations, cancellation. So the only thing that doesn't cancel in this way are edges that were not slices that you made. Right? Slices that were part of the original boundary. These are the only things that don't just disappear in a puff of smoke. And so anyway, we made this argument last time, and the punchline is that the boundary of the original region is the sum of the boundaries of the pieces that you slice up the original region into. And then, take a line integral around everything in sight, and you get this equivalent statement that the boundary line integral around the original region is the sum of the boundary line integrals around the individual pieces that you sliced up the region into. Okay. And so this was the foot in the door. This is the thing that gets us started, and then you argue that the limits are free. Can divide and multiply by area for free. This starting to look a lot like a double integral, right? The left and the right. The question comes as, what is this integrand? And sure, we don't recognize it. Okay, so what? That's, we didn't get that lucky. But even though we can't recognize it immediately, it is something that can be computed. And again, I don't want to get into the details. I consider that to be kind of the weeds in this context. There are details there that are not as important as the other things we're talking about. So this is how you compute that integrand, and thus this statement becomes this statement. And this is Green's theorem. Okay, so we talked about this last time, and we fit it. I made up this notation, which again I think I may have completely made up on my own. I'm not trying to take credit for it. I'm just trying to, if you write this outside of the context of this course and no one knows what you're talking about, that's why. Because I think I may have made this up. And anyway, but it's nice to have a name for it. But outside of the context of this course, everyone will write dq dx minus dp dy. Okay. We put it in the context of the diagram. And this is about where we left off last time. I guess one last thing I'll remind you of is that this theorem fits the pattern of the previous two of these kinds of theorems that we've talked about. And I like to call these boundary theorems, because they all involve something and its boundary. Sometimes I like to call these accumulation theorems, because all of these theorems come from the idea that something that we think of on the boundary is being accumulated over the interior by chopping it up. Okay. Anyway, the pattern, though, is that if you have some region, you take the boundary, and then based on the conventions of that column, you compute that. If you then take the integrand from that calculation, if you apply Green's operator, and for the conventions in that column, you compute that, and you get the same thing. Right, so the exact same pattern on the diagram that we originally sort of observed for the fundamental theorem of calculus. And then we observed that, hey, well, kind of mimicking the strategy and hoping we get lucky, we ended up with the fundamental theorem of line integrals, followed the exact same pattern. And now, even more adventurously, trying to apply not only in a different context, but with different dimensions. Applying the same pattern of ideas, we get yet another theorem, Green's theorem, that follows the exact same pattern on the diagrams. So, by the way, we're starting to see why now I'm such a big fan of these diagrams. Organizing these objects in this way is what allows for you to see this visual pattern. This pattern that visually demonstrates what all these theorems have in common with each other. Only comes about because we've organized these objects, these players in the game, on this diagram in this way. Okay. And just for your curiosity, most books don't draw this diagram like this. This is my own little sort of choice in how to present these ideas. Okay. All right. So now that we've got Green's theorem written down, let's do one. I'll remind you the last thing I said last time was that even though Green's theorem equates a double integral to a line integral, and even though with fundamental theorem of line integrals we tend to go this way with it, we tend to start off interested in a line integral and rewrite it in terms of a function. Namely, we tend to push things to the left. With Green's theorem, we tend to push things to the right. There are exceptions, but very often it's just the theorem goes that way. And of course, it doesn't matter, right? If two things are equal, you can use this to compute that, or you can use that to compute this. It's a matter of which is more convenient. I'm just observing that very often it's more convenient in the unfamiliar direction. Okay, so here is such an example. Let's compute a line integral of this vector field over that curve. All right, we've got a vector field, got a curve. Now, before I get into the solution, let me point out to you that notice nowhere in the question does it say use Green's theorem to compute this line integral. So there are several options that you could try or that you could consider as alternatives to Green's theorem. And you have to decide which one of these methods is going to be most appropriate for this context. So let's go through the list. One possibility, this could be a Chapter 5 problem. It could be the intention that you parameterize this curve. It would be that hard to parameterize. And that you take that parameterization and you plug it into the vector field and you do the whole pullback thing, right, a la Chapter 5. And that you, plug and chug. Maybe that would be the way to do this problem. Now, I'll make the observation that because this is a unit circle, that means when you parameterize that unit circle, x and y are going to be trig. That means that you have e to the power of trig. And you have arctan of trig. This is starting to look undesirable. It's not undoable, but it's undesirable. Right? So let's call that Plan B. Right? Let's not just plow forward. Just because you can do it with Chapter 5 methods does not mean that you should. Okay, so now what's another option? We could say, a line integral of a vector field. How about the fundamental theorem of line integrals? Right, again, seems like the perfect situation to try to use the fundamental theorem of line integrals. And you can try that as well. That's even harder, as it turns out. As in, it's impossible. Because if you try to find the anti-gradient, keep in mind that's the first step. to applying the fundamental theorem of line integrals is you got to take that vector field and find the anti-gradient. It will turn out to be one of these contradictory, impossible, there is no anti-gradient in this case. And I'll tell you later why I know that. There is a cute trick involving ideas I haven't shown you yet that allows you to immediately determine that there is no anti-gradient here. Okay. So anyway, those are options, and you got to kind of explore those possibilities. Look at all your different options of how you might compute a given thing, and then choose the one that seems the most reasonable. Okay. All right. So let's use Green's theorem. Now, Green's theorem is also comes with an asterisk. Y'all may recall that when we wrote down the fundamental theorem of line integrals, I noted there's an asterisk. The fundamental theorem of line integrals will not compute just any line integral. It will only compute line integrals of gradients. Said differently, your vector field has to have an anti-gradient. If there is no anti-gradient, fundamental theorem of line integrals doesn't even apply. Right? It's no comment from the fundamental theorem of line integrals. So you gotta know, you gotta get lucky, I guess, and your integrand has to have an anti-gradient. Well, there's a similar asterisk here, and that is, and you can see it right here in the statement of the theorem. There's no constraint on your function, particularly your vector field. Whatever your vector field is, just apply Green's operator. There's no question as if you can apply Green's operator. The question is, does your domain well, let me say it this way first. Is your domain a boundary? Right? Again, you can see it right here in the statement of the theorem. This does not say any old line integral you might find of, with no constraint. It says explicitly the domain's got to be a boundary of some region. So the way I like to say this sometimes, just for kind of grammatical consistency, is, does your domain have an anti-boundary? Everybody see where I get that term from? Right? Anti-boundary is the thing whose boundary is the... Okay. Right. That's another one I think I may have made up. If you say anti-boundary outside of my class, people might wonder what you're talking about. So anyway, you can explain it to them. Okay, so we have to look back at this question here and now decide, whoa, hey, slow down. Is this curve a boundary of something? Or said differently, does this curve have an anti-boundary? So let's draw the picture. Here's a plane. And let's see, our curve C, the unit circle going counterclockwise. So here is our curve C. And now, by the way, you're welcome to use your geometric intuition for this sort of thing. We ask the question, is this curve a boundary of something? What is this curve the boundary of? And conveniently, it's a boundary of the unit disk. And just visual case, there it is. So I'll make the observation that even though this curve is clearly a boundary, it's certainly not the case that all curves are boundaries. Here's some examples of curves that are boundaries. Oh, I keep hitting the wrong button there. There's a curve that's a boundary. Here's another curve that's a boundary. Now you might think, oh, but it's going the wrong direction. Okay, fine. So it's the boundary then of the negatively oriented, interior that it's kind of fencing off there. So that's a boundary too. Here's a curve that is not a boundary. It's not a boundary of anything, right? It just fail. Everybody see what I'm talking about? Okay, so one way that you can kind of, this is approximately true. This is close enough to true. It's not 100% true, but it's close enough to true for our purposes. But curves that don't close can't be boundaries, right? And curves that do close are boundaries. They're boundaries of what they enclose. Right. So you can just ask yourself, again, there's some counterexamples, and I'll talk about them later, but they're really not very important for this purposes of this class. If a curve starts and ends at the exact same point, then it's a closed curve and probably a boundary, and mostly a boundary. Again, for the purposes of Math 212, yes, it's a boundary. Asterisk, again, to be discussed later. Okay, so anyway, here we are. Curve, clearly a boundary. We know what it's the boundary of. So here we go. This curve, being as it is a boundary, notice that I can rephrase the question from, compute an arbitrary line integral. I can rewrite the question now as compute a line integral over a boundary. And computing a line integral over a boundary, Green's theorem. Right here. Green's theorem applies because there is an anti-boundary. Is everybody on board with me? Okay. And now it's all over with the shouting. You just kind of plug in. I apply Green's operator. Green's operator says take Q, take its x partial, take P, take the y partial, dq dx minus dp dy. Notice that's what the formula for Green's operator. And do that integral over the interior. By the way, this is an easy calculation and turns out to be 2. We got lucky, I'll admit. And this then becomes a really easy integral. 2 times the area of that unit disk, which is, of course, well known to be pi. So 2 pi. Everybody happy? Okay, so this is much better than the parametrizing method, which looked like it was going to be a nightmare. The fundamental theorem of line integrals doesn't even fit. Green's theorem crushes it. Okay, so by the way, let me just remind you again that ideas that we present later in the course are not necessarily intended to supersede ideas that we presented earlier, right? Sometimes Green's theorem is more relevant and more useful than the fundamental theorem of line integrals, and sometimes vice versa. Sometimes the fundamental theorem of line integrals will crush it, and Green's theorem will be either inconvenient or, again, won't even fit. Right? So this is not to replace the fundamental theorem of line integrals. This is an alternative. This is another tool in the toolbox. This is a screwdriver. The other theorem is a hammer. They're different. Okay. All right. Here's another one. Line integral. Got a vector field given. We got a curve that's defined in an awkward way, but anyway, it's this collection of this sequence of line segments. Compute the line integral. Now again, we have lots of options. You could chapter 5 this question. You could parameterize. The problem with the parameterizing approach is that this curve has 4 kind of separate chunks, and you'd have to parameterize each chunk separately, thus giving you 4 integrals to compute. Not impossible, but again, let's call that plan B. That sounds tedious. What about the fundamental theorem of line integrals? Does this vector field have an anti-gradient? Again, I haven't given you methods yet to answer that question other than to play the game, right? Try to go through the process of trying to find the anti-gradient, and again, I claim that once you write that all down, and this is a good exercise, everybody should do this, you will find that it is a losing game. There is no way to find an anti-gradient. There is no anti-gradient. Okay, so let's consider the possibility of Green's theorem. Now, Green's theorem, again, same asterisk. I have to ask, is this curve a boundary of something? And yeah, sure. And you can see it right here. It's a boundary of this region that comes in 2 chunks. So we can apply Green's theorem. Everybody on board? Now, we got to be careful with one thing. I say it's the boundary, but we got to be careful with orientations. Notice how I have these arrows drawn here. Again, first chunk, second chunk, etc. Notice that means that when I talk about the boundary of D1, right? Let's say, what is the boundary of D1? The boundary of D1 is that, and that, and that, which is kind of, if you will, 3 of the 6 pieces that we're interested in. So cool. Boundary of D1 gives us half of the curve we want. But now let's think about the boundary of D2. Here's D2. And let's write down the boundary of D2. Now I remind you, there are rules, very strict rules. In order for all the cancellations, you got to think about the orientations. Everything's got to be done exactly a certain way for for the Green's theorem to work, right? And one of the rules is boundary means counterclockwise, right? We talked about that a while ago. So when I say boundary of D2, notice that has me go in the wrong direction, right? The original curve that I'm interested in goes that way. The boundary of D2 goes the other way. So if I were to say, oh yeah, this curve is the boundary of D1 plus D2, that's wrong. I got my orientations backwards on the sort of the right half. So the way we resolve this is we consider not D2, but we consider negative D2. Right? What would be the boundary of negative D2? Well, remember, negative just means everything's backwards. So the boundary of negative D2 is not counterclockwise. It's the opposite of counterclockwise. It's clockwise around D2. And clockwise around D2 is exactly the right orientation in all pieces, right? We're going that way on that piece, that way on that piece, and that way on that piece. So got to be careful with this. Always think very carefully about orientations on, are the boundaries going the right way? It's not a question only of, am I fencing off a region? Do the sheep get away or do the sheep get out? That's not the only question, right? There's also this question of, is the curve oriented the way that boundaries are supposed to be oriented, and then worry if you might have to modify appropriately. So that's the big lesson here. The lesson is that our curve is the boundary of D1 minus D2, not D1 plus D2. Okay, so you see that right here. Our curve is the boundary of D1 minus D2. It is a boundary, though, and so therefore I can apply Green's theorem. Green's operator is easy to compute. Green's operator, dq dx minus dp dy, 5 minus 4 gives you 1. And then separating that integral as a difference of two integrals, integral over d1 minus integral over d2. I have the difference of the areas of these two triangles, as it turns out, and you can, geometric argument you can make, knowing as we know where these points are, you can argue that these two triangles have the same area, therefore the difference is 0, and thus the integral is 0. So, worked out pretty nicely, as it turned out. How are we doing? Is everybody on board? Okay. Alrighty. This next example is a really good example that I'm going to let y'all read on your own. Give this a look. It turns out that certain kinds of integrals are always 0, and they are always 0 as an immediate consequence of Green's theorem. So, let me just very specifically point out. So, whenever you have a vector field where the first component is only a function of x, and where the second component is 0, that boundary line integral, which you might write like this, will always be 0. That's an easy calculation. It's a matter of writing down Green's theorem. Okay, I'll let you read the details. Okay. Here's an example of Green's theorem going the other direction. Now, I've made the case that, or I've asserted that very often we want to go this way. We find ourselves with line integrals to compute, and we want to use double integrals to compute them. Let me show you an example where it goes the other way. There is a particular double integral that sometimes is hard to compute and could be easier to compute with a line integral. So here's the example. The example comes from area. Right? And if you think about it, the area of a region, you want to compute that area there, that's a double integral. It's a double integral of 1. Right? Okay. All right. Well, if I want to compute area, namely a double integral of 1, if hypothetically, if that 1 were Green's operator on some vector field, now this is let's consider the possibility, hypothetically, if there were some vector field where Green's operator is 1, the computation of area would be the computation of a double integral from Green's theorem. In which case, I could rewrite this as line integral around this is over some region D. Line integral around the boundary of D of F. Right? And I could use a line integral to compute an area. Now, how useful is this? It turns out it's surprisingly useful sometimes. But anyway, certainly this is true. Now, in order for this to work, again highlighted in yellow, you see I need to find a vector field for which Green's operator is 1. Well, it turns out that this is not a hard task. Here's an easy one. There's a vector field for which dq dx minus dp dy is clearly 1. Right? No problem. And so, using that vector field, right, this integral computes the area enclosed by that curve. That's kind of a neat trick. By the way, very often, now of course, y'all watch the recording on this discussion, but very often this integral is written in its sort of coordinate notation. This is the coordinate line integral equivalent, integral x dy. It is, in this case, a slightly less ink. Right, so I guess I see the appeal there, right? But anyway, I remind you, whenever you see integral x dy, I encourage you to think this specifically to realize that that this is the vector field in question. Okay. All right. So great, we can compute area with integral x dy. Just whatever area you want to compute, just run around the boundary. And as you go, compute integral x dy, and magically you're going to come up with area. So now that, you could argue, sounds like work, right? Turns out that there is a special case that comes up and for which integral x dy is really easy to compute. That is, imagine that you have some region whose boundary consists of a bunch of line segments. Now look at this particular little region I've created here. I've concocted this this scenario. I ask you to compute that area, and none of the angles are right angles, and the length, the edges are all radicals. And this looks like an ugly geometry problem, right? Where how do you? Oh my God, am I going to have to compute? I guess I could break this up into 3 triangles or something, like this. But how do you compute the area of a non-right triangle? And there's ways you can do it. But Green's theorem, this sort of twist on Green's theorem, turns out to be really useful here, largely as a result of the following fact, and that is that if you're computing integral x dy, now keep in mind, you want to compute the area, you're doing integral x dy, on a line segment, integral x dy is super easy to compute. On a line segment, it's just the average value of x, just average the x coordinates of the 2 endpoints, times the change in y. That's it. Very easy, right? Super, it's 4-function arithmetic. Crazy easy. So we're going to be able to compute the area of this thing just by writing down for each edge. For this first edge, I've got to compute the average value of x times delta y. On that edge, I've got to compute the average value of x times delta y, etc. On this edge, average value of x times delta y, and just go down the list. And here's how that arithmetic works out. On that first piece, average value of x times delta y, there's the arithmetic. On the second piece, there's the arithmetic. Just what's the average value of x? How much did y change? Notice that how much y changed might be negative. For example, on L2, delta y is negative. It went from a larger value to a smaller value. And a little bit of four-function arithmetic, and boom, there's your answer. We just computed the area involving non-right angles and weird trig and square roots. We just did all of that arithmetic with trivial calculation. It's pretty cool. All right. Now I'm going to leave this as an exercise for you guys to prove this result. It is totally doable. It's just a matter of writing down really a chapter 5 approach to compute this integral. Take this integral right here. Our line segment, this L, this curve L, you can parameterize with chapter 1 methods. Right, parameterize that line segment. Plug and chug. And I claim that the result you will get will be this, otherwise known as that. It's a great exercise. In fact, I mentioned at the start of the class, I do this sometimes, that things that I announce in class as, hey, this would be a good exercise, things that I think are interesting and that you're entirely capable of doing and would be a good measure of how well you're following along in class. Those 3 criteria tend to be the criteria for questions that I put on exams. And so, in fact, this has been a midterm exam question at some point in the past. I don't remember when it was. It was a long time ago. But nevertheless, anyway, good exercise, and I hope you'll give it a try. Okay, moving along. We're talking about Gauss's divergence theorem. This is one of the biggest theorems in the course. It is also yet another shameless rip-off of the patterns that we've been ripping off for the last couple of days. So this is fundamental theorem of calculus, version 4, you might want to say. We're going to take the same pattern, that same template that we set up in talking about the fundamental theorem of calculus, and we're going to blindly, optimistically, with our fingers crossed, hope that same sort of strategy gives rise to something in a totally different context, and it's going to work great. So here's our context. Now let me remind you, we're going to go into the R3 diagram here. Of course, we already have a fundamental theorem of line integrals in the R3 context. Namely, we talked about curves with boundary points. We talked about a function for which you can take the gradient, and if you do so, then that evaluation and that evaluation give you 2 expressions that are equal. Right, so that was our sort of chart of applying the fundamental theorem of calculus strategy at that point on the diagram. Okay, so again, largely for visual effect, let me say we're going to do this now. We're going to take the exact same strategy, except in this different context with different objects. I'm going to try to hope that I can get a theorem, and just to walk through it. We're going to start with a 3-dimensional solid domain over which I might consider eventually a triple integral, right? So a 3-dimensional domain. I'm going to look at its boundary. On that boundary, so this is a boundary surface, so you might say this is going to be a closed surface, not just any surface. It's got to be a closed surface. On that closed surface, I'm going to take a vector field, and over that surface, I'm going to compute a flux, because the diagram tells me to. Right? Again, these objects, these players, have been carefully selected to do exactly the job that they're supposed to do in the context that they are. So we take a solid, we take the boundary, we do flux through that boundary surface of that vector field, and then we're going to try to ask the question, well, is there instead, let's see here, something that I could do to the vector field? What is this thing that if I were to do a triple integral over the original solid of that thing, that I would get something that equals the flux? Now, so same pattern, right? Now, this is wishful thinking right now. I don't know that I can do this. I don't know what that operator is, what it would look like, how to compute it, right? But this is, look, we figured, hey man, this strategy just keeps paying off. let's roll the dice again and hope that we get lucky. Okay. Alrighty. So, again, solid, look at the boundary, and we're going to, as we have before, we're going to ask if boundaries accumulate. That, again, is the big foot in the door. Now, these are hard pictures to draw because they're three-dimensional and the paper's two-dimensional, right? So you got to work with me. But I appeal to your visual intuition. Imagine this being a solid shape. And if I were to take this solid, chop it up, I got to slice 3 different directions, right? Slice it up, and you'd get a bunch of little sub-boxes. And the question we want to ask is the boundary, do these boundaries accumulate? So, fleshing that out, is the boundary of the original solid, I ask, the same as the sum of the boundaries of these little diced up pieces? So, do boundaries accumulate? And the first picture I'm going to draw along those lines is this. We imagine a case with, sort of the world's simplest case where we have, one region over here and we have another region over here. Is it the case that the boundary of D1 plus the boundary of D2, is that equal to the boundary of the whole thing? And, well, this edge over here works out, right? I mean, that's part of the boundary of D1, oriented that way. That's also part of the boundary of the whole thing, oriented that way. Right? So that piece is cool. This piece here is cool. Most of the pieces add up just fine. The big question is, oh, wait a second, there's this guy here. That is part of the boundary of D1. It's part of the boundary of D2, but it's not at all part of the boundary of the original solid. So when I take the boundaries of D1 and D2 and add them up, am I creating more boundary that shouldn't be there? Am I going to get whatever this green, so this S surface here, or I called it S, let's call it S. Am I going to, when I add up the boundaries of these D's, am I getting surface highlighted in green that is not part of the boundary of the original solid? This would be a massive problem. This would mean, if that were to happen, boundaries would not accumulate, we would have no foot in the door, and the whole process crashes and burns and dies. Let's think it through. Thought of as part of the boundary of D1, right? This surface is oriented that way. Right? Keep in mind, there's rules, very important, strict, careful, delicate rules that about which way orientations go. When you say boundary of D1, boundary is always oriented away from the solid. So notice I have this S1 arrow oriented away from the solid D1. Thought of as part of the boundary of D2. Let's see here. Let me do it like this. Here's D2. Thought of as part of the boundary of D2. This same face is part of that boundary, but again, oriented away from the solid, oriented away from D2. It's oriented that way. So, this surface appears twice in the summation. It appears twice, but with opposite orientations. And so they cancel. So that term goes away, and all we're left with is the stuff that's supposed to be there anyway, that is part of the boundary of the original region. So boundaries accumulate. Everybody on board? See how there's something interesting going on here. The geometry of this picture is very different from the geometry of the Green's theorem picture. And yet, morally, it's kind of the same because opposite same piece, opposite orientations cancel in the interior, leaving only the original boundary. It's the same structurally, right? But it's different geometrically. Fundamental theorem of line integrals is, again, different geometrically. They're all different geometrically, appropriate to their context, but the structure, the way the ideas fit together is the same. Okay. All right, so boundaries accumulate. By the way, yes, there are that was a special case, but let's make the same argument here. Let's talk about that face right there. That's part of the boundary of that. Oh, it's part of the boundary of this piece, and it's part of the boundary of that piece. And well, same picture. That piece cancels. What about this face here? Right, that's part of the boundary of that piece. It's part of the boundary of this piece, but with opposite orientations and cancel. So now again, the pictures are really hard to draw. I can only draw so much of these pictures, but I appeal to your intuition. All the faces that were created by the process of slicing, the nature of slicing is slice means that there's stuff on one side and stuff on the other side, and we're going to have morally this picture then happening for each slice that, in the process of slicing up. The only pieces of surface for which we don't have this picture are the pieces of surface that were not created by our slicing. Just the pieces of surface that were there in the first place, namely, like a piece of surface there, a piece of surface there. There is nothing on the other side. Right? It's part of the boundary of, this solid there, but there's nothing on the other side. There's nothing to cancel it. Okay. All right. Okay, so boundaries accumulate. Let's talk about flux. Again, that was our idea in the first place. We're going to take this boundary, this accumulating boundary. We're going to take the flux through that boundary of, some vector field, thus giving us this. There's, boundary flux through the original solid, and we just got through arguing that the boundary of the original solid is the summation of the boundaries of the little pieces that you slice it up into. Therefore, the fluxes accumulate in exactly the same way, and so we get flux is a summation. Again, you can add a limit for free. Limit of a constant is that constant. This looks a lot like a triple integral, except for there's no volume. So let's multiply and divide by volume. Right, this is looking really familiar. Same sort of strategy, just adapted to the context. Now this really does look like a triple integral. It's just that it's a triple integral whose integrand we don't recognize. That's our problem. It's not the theorem's problem. Just because we don't happen to recognize it in advance. Okay, well, so something that has to be computed. Again, it's in the weeds a little bit. There's an exercise in the homework that I'm going to have you all do where you're going to, in a very oversimplified case, I'm going to have you go through a calculation where you'll come up with this as the answer in the oversimplified case. I think it's a good exercise to give you just some sort of it's a sanity check. It's a plausibility argument that this would be right. It's not a proof. It's just an oversimplified, but morally kind of the point calculation. Anyway, you're going to come up with this as your answer. So the accumulation, the way in which flux accumulates, I can rewrite like that, and lo and behold, we have a new theorem. This is Gauss's divergence theorem. That flux can be thought of as something that accumulates over the interior. It can be thought of as a triple integral. Specifically, it's a triple integral of this thing. So, by the way, this thing, let's talk about this thing now. This integrand, it's called divergence. This integrand is called divergence. Very often written like this, div f. Mathematicians write it that way very often. I did not make that one up, right? But you could argue that this is kind of my motivation for rewriting Green's operator as GRN. It's kind of a mimic of div, short for divergence. So that's very often how it's written. It's not the only way that divergence is written. There is another shorthand notation for divergence that's, I think, kind of more common. Physicists use this next one that I'm about to show you, at least in my experience, more. So it comes from the gradient operator. Now bear with me. Divergence is not the same as gradient. Very importantly, not the same. But you all recall this is the notation we use for gradient. This is the formula for gradient, and one could, It's a little bit of an abuse of notation, you might say, but you could think of the... here, let me zoom in so we can see a little bit better here. You might think of what we're doing to F here, this thing that we're doing to F, could be thought of as this, I'm going to call that a vector operator, right? It's, we know the result is a vector. The vector result's got 3 components. I could think of the operator itself as having 3 components. And what we're doing to F is just applying that operator, 1 component at a time, to F. That's a way of thinking about it. Anyway, again, notationally a little sloppy, but with that in mind, we can think of this thing as being a standalone separate thing. Now, when you write, by the way, the terminology, they call this Dell. This is the Dell operator. When you write del F, that means the gradient of F. But the operator by itself depends on how you apply it. What do you do with it? If you do this to it, then you're taking the gradient. But that operator by itself is thought of as a separate thing. And again, the Dell operator. And there's other things that you could do with this operator. So here's the weird thing. Now, this is just notational motivation. But what we could do with this thing is, and this is going to seem strange, but I'm going to take this operator. Notice that it kind of appears there in the formula for divergence. And it's kind of like we're taking a dot product there. It's kind of like we're taking the Dell operator and dotting it with PQR, namely our vector field. This just, I'm just saying, right? But look at this construction here. Looks like a dot product. And so that motivates this notation here. Alternative notation for divergence. It's extremely common. In my undergraduate second major in physics, I saw this notation, del dot F, quite a bit more than I saw div. A lot more. So heads up, you're definitely going to see that notation, and this is the motivation for why it's kind of plausible. Please make a point of you've got to put the dot in there. It's so wrong if you just write this, and I have students every year that do this. This does not mean anything. This is garbage, and it is not an acceptable substitute. If you write this, then it's wrong. So be very, very careful about that. The dot has got to be in there. Heads up. Okay, anyway, that said, we have some sort of notational alternatives then for how to write down Gauss's divergence theorem. Just to remind you what we did, we started off by taking a boundary and then a flux. And we have now found that I can view that as a triple integral, specifically a triple integral of this thing, the divergence of the vector field, and here I am using that physics notation. Okay. All right. So same pattern. It's a fundamental theorem of calculus in this different context. Same ideas, same pattern, different theorem because of the different context. Okay. Again, that's how you're going to see it written. Unless you become a math major, I think this is probably the way you're going to see it anywhere. Okay, and again, I like to write the theorem separate from the context. I like to leave this, this original organization of our players. I like to leave there, and then the theorem separately down here. Okay. All right. So a quick example. Suppose you want to compute a flux. Here's your vector field. We've got a surface. Now you can do this as a chapter 5 problem, right? If someone say, here, compute this flux, y'all know how to do it. Parameterize your surface. Plug in, pull back. Plug and chug. So that's an option here. I strongly advise against it. Let's think it through. If you did that, if you parameterize your sphere, the best way to parameterize a sphere involves a bunch of trig. And that means that x, y, and z are going to be trig functions. So you're going to have e to the power of some trig functions. And that's going to be ugly. Okay. You're going to have some trig functions squared. And, right. You're going to have to compute the capital N vector for, where there's trig and all over the place. It's going to be super inconvenient. Okay. So here's another option. We have Gauss's divergence theorem. We've been asked to compute a flux. Maybe I could just turn it into a triple integral. Notice that in order to turn this into a triple integral, I'm going to have to take my original flux and I'm going to have to compute the divergence of it. Okay, that's not a problem. We're assuming, by the way, in this chapter that all of our integrands, all of our vector fields and functions, that everything in sight is continuously differentiable and there's no regularity issues. As a first time through the material, I think that's very reasonable. There are some really interesting counterexamples when they're not. But anyway, that's a digression. So, sure, whatever vector field we have, we can take the divergence. The question, the asterisk, all these theorems have asterisks. Notice that if I want to compute a flux, this theorem only comments on fluxes through boundaries. That's not a subtlety. This is super important. If you are trying to compute a flux, and if it's not a boundary, then what you got, it doesn't fit. It doesn't make any sense at all. Specifically, not only does this have to be a boundary, you need to be able to find that anti-boundary. It is that anti-boundary over which you do the triple integral. If your surface is not a boundary of anything, then there is no triple integral to compute. Right? So, it's really important that you got to make sure that that your not only that your surface is a boundary before you apply this theorem, but that you know what the anti-boundary is. Does everybody see what I'm talking about? And the reason I make such a big deal out of this one, by the way, notice it's morally equivalent to a point that I made about Green's theorem. Right? Same point. The reason I make such a big deal out of it here is that it happens every year that a question will come up on the exam or on a midterm or whatever, where the question is to compute, the flux through blah blah blah. That's not a boundary. And students will do the following argument. Students will say, "Oh, well, we were asked to compute a flux. Gauss's divergence theorem says fluxes are triple integrals." And they'll compute the divergence, and sometimes the divergence is equal to 0. And they'll write 0 and spike the football and move on to the next page. But the gaping hole in this argument is they made no comment as to what the surface was and no comment as to what the domain of this integral is. If the question is to compute flux through a non-boundary, there is no, this is complete garbage. A lot of students say, oh, well, partial credit, I correctly wrote down Gauss's divergence theorem. It has nothing to do with the question, right? Very importantly, there is, if your surface is not a closed surface, then there is no anti-boundary, and this is completely disconnected to the question itself, right? So this is one of these heartbreaking things for me, but I am obligated. I hate doing it, but I'm obligated to give 0 points on this because it's got nothing to do with the question that was asked. Everybody see what I'm talking about? So be ultra careful on this. This is a total landmine. It's so tempting. You see, psychologically, you're like, oh, flux, triple integral, the divergence is 0. You see the daylight, you run toward it. Please don't. It's a trap. All right. It's a landmine. Okay. On the other hand, if this is actually a boundary of something, then there's no question there is an anti-boundary, and this is awesome. Right? So I'm not saying don't ever cite Gauss's divergence theorem. Gauss's divergence theorem is is super convenient. It's super powerful. I'm a big fan. If it applies. So, heads up. Enough of that speech. Okay. So let's go back to the question we're considering here. We want to apply our theorem. We want to compute a flux. Here's a vector field, unit sphere. We've agreed parametrizing would be a nightmare of algebraic inconvenience. So let's look at this domain here. The sphere in the unit sphere in R3 oriented outward. Draw a picture. The unit sphere. You know what? I made a poor choice of color there. Let me reconsider. The unit sphere oriented outward is this surface. That. Yeah. Okay. Okay, so I've got a flux. Gauss's divergence theorem can compute flux. The big worry, check for landmines. Is my surface, I ask, is it a boundary of a solid? By the way, let me do another sort of brag on this diagram. The diagram tells you what you have to ask. Right? The diagram says, if I want to rewrite that integral as this integral, I'm going to need my surface. There needs to be, this diagram's got to fit. There's got to be a solid whose boundary is my surface. It's what the diagram says, right? So I'm a big believer. I hope y'all will, use this diagram, try to internalize this diagram as much as you can, because it helps you. It does work for you. It remembers things for you. Okay. So is this surface a boundary? Sure. But no proof required. It's geometrically obvious. This surface, the outward-oriented unit sphere, is the boundary of the unit ball. Solid unit ball. Terminology reminder: sphere means surface, ball means solid. You got to be careful with that terminology. It's really easy to mess that up. Okay, is everybody on board? Did everybody see how this sphere is clearly the boundary of the unit ball? So seeing as it is a boundary, I can write Gauss's divergence theorem. There's Gauss's divergence theorem. All I have to do now is compute the divergence of this vector field. This divergence is really easy to compute. I got to take the x partial of that plus the y partial of that plus the z partial of that, like so. Easy algebra. Good fortune. A lot of the ugly disappears taking those partial derivatives, and we end up with the divergence being just 2. And so the flux integral that we were asked to compute at the start of this question turns, okay, fluxes are kind of hard to compute sometimes. We've rewritten as a triple integral, which themselves are kind of hard to compute sometimes, but in this case, this ugly flux is rewritten as a trivial triple integral. Namely, an integral of a constant over a garden variety, well-known, geometric figure. And so, arithmetic. Everybody happy? We won't always get this lucky. It doesn't always work out this well. Not every tool works in every situation. This is a ratchet wrench, right? We already had a screwdriver and a hammer. Ratchet wrenches are great. They're just the perfect tool in a lot of situations, but if you need to pound a nail into wood, full confession, the ratchet wrench is not what you're looking for, but sometimes, right, like in this case, it's super useful. Okay, so there's another piece of terminology that I need to explain, and I think this is fantastic terminology. I love this terminology, and I want to motivate it by starting with what's going to seem like an odd interpretation of the fundamental theorem of calculus. And let me remind you, having a point of view on understanding something is nice, right? But there are other points of view that can be super powerful. Like, so for example, derivatives. Y'all understood derivatives before you came in here as, slopes, for example. Right? And that's a fine way to think about derivatives. But I urge you to reconsider, and to great effect, we reinterpreted derivatives as being relationships between input changes and output changes. Right? And it was that point of view that allowed us to make sense out of the idea of the derivative transformation and the Jacobian matrix and input vector, output vector. Directional derivatives ultimately come from this idea of derivatives being relationships between input changes and output changes. Okay, so here's a new point of view on derivatives that is going to be super useful in this context. So anyway, again, I apologize for telling you a bunch of stuff you already know, but the point here is not to tell you stuff you don't know. The point is to give you a different way of looking at something you already know, and it's going to be super valuable. So here we go. All right, fundamental calculus. Yawn. All right. Okay, let's look at the left side of the equation here. This f of b minus f of a. I argue that says how much did the function change between a and b, right? It was f of a. It became f of b. The amount that the function changed is exactly this. Okay, so I'm going to use this notation, delta, very common choice, delta, to represent changes, right? So not delta x or delta y, or just delta, just as a label to put on what is this object. And now I remind you, we've already taken the point of view on the fundamental theorem of calculus that it's an observation about an accumulation, right? That these changes accumulate. And by the way, let me switch to a different picture here. This is a page that it's not in the book. This is a separate page that I've written. I owe you an email to email you this PDF document. If I don't send this email with today's announcement about what homework we're done with, please remind me. If I forget, it was completely inadvertent. But you can see the change. If a function does this, well, the value of the function was this value, and it became that value, and you can see the change right there. You can further see change accumulating. Right? So between here and here, the function didn't change at all. But between here and here, the function changed by that amount. And then between here and here, the function changed by that amount, etc. Right? So the total amount of change is the sum of the amounts of change that you see on each little piece of the domain from A to B. Right? This is again pretty believable thing. I like the metaphor of my height as I was growing up. Right? Imagine here's my height at age my height at age 2, I don't know, right? And then I don't know, this is not exactly but maybe, okay, so here's my height at age 2, and here's my height at age, 20? I don't know when people stop growing. And so this process, my height changed by that amount, right? But that change was not an instantaneous thing. I compute change as f of b minus f of a, height at age 20 minus height at age 2. That's how you compute it. But it didn't just happen, right? The process of my height changing, well, I grew a little bit each day. And the sum of how much I grew each day, right? You add up all those little, small changes. That's the sum of all those changes gives you the total change in height over those ages. Okay. So change accumulates. It's a statement about an accumulation of a certain quantity, and the quantity that's accumulating is change. Okay. All right, so going back to this point of view, right, we have this quantity that's accumulating. Accumulations are written as integrals, which have an integrand. Now, where have we seen this situation before? Where have we seen the idea of a quantity that accumulates thought of as an integral with an integrand. And mass. Mass. Imagine a one-dimensional rod, right? That has mass, non-constant density. You want to talk about the total amount of mass. Well, the total amount of mass is the sum of the masses in each little piece. There's this accumulation. It's thought of as an integral with an integrand. So, just for your consideration, it's a different way to think about the fundamental theorem of calculus as an accumulation of change. And I think this is a really nice way to think about the fundamental theorem of calculus, an accumulation of change. Think of change as kind of physical. It's not, of course, it's not physical, but think of it as kind of physical. It has properties just like a truly physical quantity, namely mass, in that it accumulates. Right? So go ahead and think of it that way. Think of change as being a kind of physical, kind of a stuff sort of a thing. Okay, so with that in mind, thinking of change as a kind of a stuff, in the same way that we refer to this integrand as mass density, I'm going to propose, preposterously it seems, that we think of the derivative as being change density. And so it's kind of a broad application of the notion of density. And keep in mind, density means stuff per unit size. Could be all kinds of different things. We talk about population density. It does not mean how dense is the population, right? Population density means there's a certain kind of stuff, quantity of people, and how much is that quantity, per unit size, typically area, right? So stuff per unit size. We're thinking of change as a kind of a stuff. F prime is stuff per unit size in this case. It's stuff per unit length. And so you can think of it as a kind of a density. And this is again stretching the notion of density. Typically, density refers to a visceral stuff, a physical stuff. Here we're applying the notion of density to a more of an algebraic stuff, but it behaves like a stuff, so we're going to describe it like a stuff. Okay. All right. So now let me go back to the diagram I have here. Again, I owe you an email. Let's talk about, where is derivative on this picture, and what does that have to do with anything? Well, I want to talk about how the accumulation happens. If, the function changes like that, and you say, well, change is f of b minus f of a, and I ask you, where did the change actually happen? The naive answer of where did the change happen would be to say, well, between A and B. We were at A, we ended at B. Between A and B, here's the total change. Well, come on, right? When did I actually grow? Did I just sort of magically grow from age 2 to age 20 and boop, and up, change in height, and that's it? No. My change in height happened over, a little bit each day for, however many years that is. So, likewise, even though we measure change by looking just at the endpoints, that's a super naive point of view on where the change actually happened. You can see it in the picture. It's perfectly obvious. There's the change happening. It's over this part of the domain that the change actually happens. There is no change happening here. There is no change happening here. It happens in the green region. Right? Everybody on board? And so here's what this has to do with derivative. Derivative is literally telling us, by way of interpreting derivative as change density, it's telling us how much change density there is at any given place. So, for example, let's look at this point here. At that point, if I want to compute the derivative, then I draw this little, try to draw a better triangle. Draw this triangle, and you can see we have change is the rise, and size is the run. For a piece of the domain of a given size, given some piece of the domain of a given size, change density, change per unit size, quantity per unit size. So change density is, it's rise over the run. It's the slope. It's the derivative. Derivative is literally telling us, by way of, whether it's large or small, how much change is actually happening in a given place. It's telling you how much of this stuff. It's telling you the density of this stuff at that given point. Is everybody on board? Okay, so now I know this is a weird point of view to take, and again, I warn you against the temptation to think, I'm just going to choose to think of the fundamental theorem of calculus in the way that I'm already comfortable with it. It's not the point. I'm not trying to teach you the fundamental theorem of calculus. I'm trying to give you a point of view on which it's easy to draw pictures and with which we can relate to experience of how things change. Is really easy to relate to set up an analogy. And so now we're going to move on to the analogy. I'm going to go back to the book here, and let's go back up to this. Here's our Gauss's divergence theorem. Right? And I'm going to argue the same thing. Flux accumulates. And accumulates over a solid, right? This is where Gauss's divergence theorem came from. Flux accumulates over a solid. So it accumulates as a triple integral. And it's a triple integral of a certain integrand. Now, where have we seen this before? Where have we seen, in a three-dimensional context, where have we seen stuff accumulating over a solid as an integral of a certain integrand? And I argue that, we've seen it in terms of talking about mass. Mass is a kind of a stuff, right, that accumulates with a triple integral of a certain integrand. And in the same way that we refer to this integrand as mass density, mass per unit volume. It's a three-dimensional context, so this is, a slightly different kind of mass density. But anyway, the integrand being the density representing how mass accumulates over the solid. Divergence, I'm going to rewrite as flux density. So in the same way that mass density represents how mass accumulates as a triple integral over a solid, flux density represents how flux accumulates as a triple integral over a solid. Same way. Okay, so this is a really important point of view on divergence. Divergence is not just some algebraic object that, part of the, it's not the word abracadabra in the magic trick that just magically makes the magic trick work. Divergence is a specific thing. It's telling you something very literal about the thing that you're computing. In the same way, so mass density, this density thing here is telling you where the mass is. It's telling you how mass is accumulating over that interior. In the same way that the derivative is telling you how change is happening. It's telling you how change is accumulating over that interior. Divergence is telling you how flux is accumulating. It's telling you how much flux is accumulating at a particular point in the region over the interior. There's a very, literally, physically important thing. So this term flux density just perfectly encapsulates what's going on there. That how to think of divergence as measuring locally how much how much stuff per unit size. Thinking of flux as an accumulation of stuff. How much flux per unit size is happening at a particular location. So you're going to see this term a lot. Flux density, again, very, very common in physics and engineering. I think, if my memory serves, that I heard the term flux density about as much as I heard the term divergence in my second major in physics. Mathematicians say divergence, but from a physics point of view, it makes a lot of sense to say flux density. So you're going to hear that a lot, and of course, it's also a really good intuition for how to think about things. Let's see here. So, by the way, here's the picture of that. And I need to talk about this, but let me just make a reference to the second page of this document. I'm going to use this picture, analogous to how I use this picture, to talk about how divergence tells you where flux is happening. We're going to argue that even though we compute flux on the boundaries, that's where you compute flux, right? Of course, fluxes are computed on boundaries. That's been the whole point of Gauss's divergence theorem. But we're going to interpret divergence as telling us, yeah, but this is where that flux, even though I detect the flux on the boundary, this is where the flux actually happens. And I owe you an explanation of, how does that come through. We'll talk about that next time. Okay, see y'all later.